in the last class we have discussed that relations between edge length, radius and diameters of a crystal lattice. We have discussed the relations between radius, between the edge length and the diameter of a crystal lattice. We have done some questions on it, as well as we have done some NEET examinations question paper also. Few questions we have solved it, right? Today also we are going to take up one question, the question which you can see on the board. It is from Nagaland Board of School Education. Okay, this question is in NBSE. It was asked in NBSE in 2013. So we are going to solve it. It's very simple questions and it was asked for 3 marks. Okay, so now let's start. Okay, and if you are new to the channel, if you have not subscribed, please don't forget to subscribe the channel and share the videos with your friends. Okay, so here it is given what? The length of a unit cells. Okay, the length of a unit cells, the length of a unit cell edge of a body centered cubic metal crystal is this much. That means length of or the edge of a body centered. That means I have already told you edge is what? Nothing but it is represented as 352 picometer it is given. So let it be in picometer only. They are telling us to calculate the radius of a crystal. Very simple it is. If you remember the formula for NBSE, then you will be knowing it. We know that relations between A and R for BCC. So relations between A and R, we know the relations, we can write like this, we know relations between A and R for BCC is what? You can write R is equals to root 3 by 4A. This is the relations. Okay, last class I have told you what is the relations for BCC in the case of this what do you call, edge length and radius calculation. So here it will be R equals to root 3 by 4 into what is the edge length? It is given 352. So here 4 8s are 32, 4 8s are 32, 4 8s are 32. So here what it will be? It will be root 3 into 88, which means root 3 value is what? 1.73 into 88. So if we multiply it, then 1.733 into 88. So 24, 56, 58, 8 and 13. So it will be 4, 8, 3, 1. 1, 12, 11, 12, 4, 5, 1. So the decimal is after 2 digits, so we place it. So it comes to the radius will be how much? 152.24 picometer. So then this is the answer for these questions. Okay, now we shall move on to the next topics. Okay, based on this topic we have done some questions. We have also solved the NEET questions based on this topic. Now we shall move on to the next topic. So the students, you can pause the video and take down the answers. Okay. Okay, hope you have taken down. So all of you are studying well, I hope. Okay, fine. So next topics we are going to do is we are going to understand is closed packing structure, closed packed structure. So the topic is closed packed structure. Okay, so closed packed structure is what? See, the closed packed structure means you can say that the molecules or the here the atoms and all, they will be very much close to each other, okay, in a closed packed structures, those structures in which the atoms are very close to each other, okay, those we will be calling it as what, closed packed structures. Okay, there are different types of, there are three different types of closed packed structure. The first one is one dimensional, okay, one dimensional packing. One dimensional, you can say packing, or you can say one dimensional closed packing. One dimensional closed packing, let us say closed packing. So what does it mean? Let's assume that this is a x-axis and this is y-axis, okay, got it? In one dimensional closed packing means what? The atoms will be arranged in a straight line like this only. So here it will be arranged in this way, got it? So here you can see very clearly that the atoms are arranged in what? In a straight lines, okay, you can see that the atoms, they are arranged in a straight lines. So this kind of arrangement we call it as what? One dimensional closed packing, okay, one dimensional closed packing, okay, got it or not? Good. Okay, fine. Next one we are going to see is, okay, the second one is closed packing in two dimensions. Second one is what? Two-dimensional closed packing. So two-dimensional closed packing, okay, two-dimensional closed packing. So in two-dimensional closed packing, how the atoms will be arranged? See, this is your x-axis, this is your y-axis. So here in two-dimensional, see, one-dimensional simple thing I am telling you, the molecules or the compounds or the atoms are arranged only along one axis, only along one axis. So this arrangement will be called as what? One-dimensional arrangement. Two-dimensional closed packing means what? The molecule, the atoms here, it will be arranged along x-axis, we are arranging it, as well as along y-axis also we are arranging it. Got it? So the arrangement is along y-axis as well. Are you getting my point? See, along x-axis as well as along y-axis. That means here we are using two dimensions, x and y-axis we are using. So this type of closed packing we call it as what? Two-dimensional closed packing. Okay, so arrangement here is along two axes. Okay, so here arrangement is done along what? Two axes. So this one will be called as what? Two-dimensional closed packing. Okay, two-dimensional closed packing structures. Point is clear, dear students, I think. Now let us go to the three-dimensional closed packing structures. Okay, fine. Three-dimensional closed packing structure. See, three-dimensional closed packing structures is what? Let us discuss third one, 3D or three-dimensional closed packing structure. Very simple, these are basic things, so just let's do it quickly. Okay, and it's revisions. So three-dimensional closed packing structure. In three-dimensional closed packing structure, you will see that, okay, x and y. This board is a two-dimensional, so it will be a little difficult for you to, for me to tell you. You have to imagine it. Okay, 1, 2, 3, 4, 5, 6. This is along one axis. This is along y-axis. So this is along y, x and y, plus one over this. This is one like this. If you imagine one in this directions and one in this directions, we have arranged it. Now over that arrangement again we are putting it. Suppose let's assume that I am over this arrangement again. I am putting the atoms, number of atoms. If I am putting like this again over these arrangements, then what will happen? You will see that this is like this, then we have arranged in this way, this way, this way, this way we have arranged. Now over that again we are making another layer, again over that again we are making another layer, over that another layer. So if layer after layer if you make, then you will see that the height also will be there. X-axis, Y-axis we have arranged, and now over the bottom layer we are placing another layer, again another layer, another layer. Then you are getting third axis also, that is Z-axis, X, Y and Z-axis, that is height also will come. If you are arranging it layer after layer, so height also will be there. So that kind of arrangement we call it as what? Three-dimensional arrangement. Why? Because there we are using three axes. One is what? X when we are arranging the atoms in this way, one is Y when we are arranging the atom in this way, and Z is what? When we are forming a layer after layer heap we are making, so it is getting a height. That means it is a three-dimensional close packing structures. Okay, dear students? Okay. Now one thing, when we are doing it, when we are arranging the atoms in a close packing structure, just imagine, see like this way we are arranging. Then you see one thing, all they are touching each other, but still there is a space left in it. This space, the empty space in between them, this is called as what? Void. Okay, this is called as void. So there are two types of voids are there. One is called tetrahedral void. Okay, tetrahedral void. Another one is called as octahedral void. Okay, so one is tetrahedral void, another one is octahedral void. So what is the void? Void is nothing but an empty space between the atoms in a close packing space. If there is an empty space, that empty space we call it as what? Void. And two types are there, tetrahedral and octahedral voids. Okay. Okay, dear students? Okay, fine. So hope you have taken now. So now we have done two crystal close packing structures. Okay, close packing structure is done, and okay, so now we are going to study how many tetrahedral and octahedral voids are there. Okay, got it. So the topic here now it is number of closed, okay, number of octahedrals void, number of octahedral void. Okay, number of octahedral void is equals to n, where n is the structure of n sphere. Number of octahedral void is equals to n, where n is a sphere. So that means what? In an octahedral, so the how many number of voids will be there? The number of voids available in an octahedral, it will be how much? N. Okay, n voids will be there, n sides will be there, which will be empty. Now number of tetrahedral, okay, tetrahedral void, okay, number of tetrahedral void is equals to 2n, twice the number of sphere, where n is a spheres. Okay, twice the number of spheres. Okay, got it or not? So number of octahedral void or site is equals to how much? N, where n is a sphere, and number of tetrahedral void is equals to 2n. So if I ask you combine octahedral and tetrahedral void, what is the total number of void? So total number of voids will be equals to how much? 2n plus n. So it will be equals to 3n. Okay, dear students. So what is the number of octahedral voids? N. And what is the number of tetrahedral void? 2n. And what is the total number of void combining octa and tetra? It is 3n. This point you can note it down. Okay, fine. Now we are going to study about very important point that is called as coordinations number. Coordination number is what? Let us try to understand it. So okay, what is coordination number? Let us try to understand. So it is the closest neighbor of any constituent particles in the crystals. So what is coordination number? It is the closest, okay, neighbor. It is the closest neighbor, okay, of any constituent crystal, of any constituent crystal. Got it? It is the closest neighbor of any constituent particles in a crystal. Any constituent particles in a crystal. Particles in a crystal. Okay, now what does it mean? Suppose there is one constituent particle 1, there is another constituent particles 2, and there is another constituent particles 3. Now if I ask you what is the coordination number of 2, suppose if I ask you what is the coordination number of 2, so you write coordination number of 2 is equals to, how many are they touching to this 2? There are 1 and 3 is touching, so they are called as what? Coordination number. Therefore the coordination number of 2 is equals to 2, because it is being touched by how many atoms directly? 2. So the coordination number is 2. Hope you have understood. Now let's take another examples of coordination numbers. Suppose 1, 2, 3, okay, 4, 5. Okay, suppose 1, 2, 3, 4, and this one is 5. So if I ask you what is the coordination number of 5, so how many constituent particles are touching to 5? 1, 2, 3, 4. So the coordination number of 5 is equals to 4. 4 are touching directly to 5. The fifth sphere is being touched by remaining 4. So the coordination number is 4. What is the meaning of coordination number? It is the closest neighbor. So these are the closest neighbor to 5. So that will be the coordination number. I hope, dear students, you have understood what is coordination number. Okay. Okay, fine. Now next we are moving on to the closed packing efficiency. Okay. Closed packing efficiency. So this one derivations we will not be doing. Closed packing efficiency. That means what? See, closed packing efficiency means what? Like in BCC structure, suppose there are different types of structures are there. That is simple one, simple, okay, simple lattice, then BCC structures, okay, simple one, then it comes BCC, body centered, then it is called FCC, then it is comes HCP, hexagonal close packing. Okay, so you will see that in simple primitive cells, the packing, close packing structures. See, this is the one arrangement. Okay, so how closely they are attached to each other. Okay, there should not be any means how much space out of 100, if you see how much space they have packed it and how much space is empty. So that is the meaning of packing efficiency. So we are doing a topic about packing efficiency. Okay, that means what? How efficiently the packing can be done in all these 4 arrangements. Got it or not? Simple cubic cells, body centered cubic cells, then FCC face centered, then hexagonal cubic cells. Okay or not? So in all these 4 arrangements, what is the close packing structures? Means how much space the spheres occupies and how much space is left behind. So remember, dear students, the closed packing structures in volume occupied. So always remember, let's write it one by one. This question used to come in your board exam for choose the correct. Also in the competitive exam as well, you will be getting these questions for choose the correct, and it may be for 4 marks. So always remember, the first thing we are going to write is what? Volume occupied in FCC. Okay, so volume occupied. Okay, occupied by whom? By the particles. Okay, volume occupied by whom? By the constituent particles. Okay, so the volume occupied by constituent particles in FCC, face centered, or we call it as another name of FCC is what? CCP. Okay, CCP arrangement. So this one you have to remember. So volume occupied by constituent particle, that sphere we have seen, that is constituent particles in FCC or CCP arrangement is equals to what? Out of 100% they occupies how many percent? 74. So if I ask you volume left vacant equals to volume vacant. So volume vacant in FCC. In FCC means how much area or is left without occupying. Okay, which is you can say that how much percent is void, means empty space. Then volume vacant in FCC equals to how much? 100 minus 74. This is occupied, so minus 100 minus occupied one, so it will come, you will get the left out one, that is 26% it is left. Okay, it's vacant in FCC. Okay, this one percentage is very important. I'm not doing the derivations because derivation is not that important, but percentage is important. It used to come for choose the correct. Okay, for next is what? Volume occupied in HCP. Okay, is also same. So volume, next one you just write volume occupied in HCP, that is also equals to 74%. Okay, so this one 3, you remember it. Volume occupied by a constituent particle in FCC or CCP arrangement is equals to 74%. Volume vacant in FCC, it will be how much? 100 minus 74, that is 26. Next one is what? Volume occupied in HCP structure, it is also equals to 74. Next, third one is what? Volume occupied in BCC arrangement. Volume occupied by constituent particles in BCC will be equals to how much percent? Will be equals to 68%. Okay, so how much percent is occupied in BCC structure? It is 68%. Okay, this one is very, very important to remember. Okay, dear students, FCC 74%, HCP 74%, CCP 74%, BCC 68%. So volume vacant in BCC equals to 100 minus 68%, so it will be equals to how much? 32%. These questions was asked in your NEET examinations 2015 or 16. It was asked how much space is vacant, how much volume is vacant in BCC structure. So it was given 32, so you have to take 32%, 4 marks. Okay. Next, question number 4, dear students. Okay, what is the question number 4? Volume occupied by simple cubic arrangement. Okay, so the fourth one is volume occupied by constituent particles in simple cubic is equals to 58%. Okay, volume occupied by constituent particle in simple cubic is how much? 58%. So volume vacant will be how much? Volume vacant, come on, tell me everyone, this is very easy. In simple cube will be equals to what? 100 minus 58%. So it comes equals to 2 and 42% is vacant. So in simple cube, we will see how much a space is vacant, 42, how much it is occupied, 58%. In BCC, 68% is occupied, 32% is vacant. In volume occupied in HCP, 74% vacant, volume vacant in FCC, 26%, volume occupied in FCC or CCP, 74%. So this 4 points is very important, dear student. It is very, very important for choose the correct in your board examination as well as for the competitive examinations. So you can note it down, okay? Pause the video and you can note it down, okay? Fine. So hope all of you have taken down, okay, and you are understanding. Next, let us go to the very important part. It is also important for your board exam point of view. It is derivations, which is generally asked in your board exam for 3 marks. From this chapter, if numerical does not come, then that derivations is sure to come, okay? So all of you can pause the videos and you can first take down. Okay, so the important questions, this is 3 mark questions. Most probably it used to come in the exam, not only in NBSE, CBSE also. So here question is what? Relations between radius of octahedral void. So this is the void. Actually you might be thinking that, sir, octahedral means 6 spheres should be there. You are drawing only for C. 6 sphere, of course it will be there, but the spheres which is on the top and which is on the bottom, that one, the board is 2 dimensions, so I cannot draw it that. So for easy diagram and for better understanding, we have considered only the 4 spheres, okay? 6 we are not considering it. The one will be there at the back as well as in the front. This side also it will be there, and that back side also it will be there, okay or not? And this is in the middle, so we have taken the middle portions only, okay? And diagram also becomes easy. So octahedral void is R. So this is the void, this is the space which is left inside it. My diagram is not proper, or else it will come as spherical, okay? This one also it will come as spherical, the void inside space, it will be spherical. And radius of the atoms, these are the atoms. So what is the radius? Capital R, capital R, capital R, capital R in a close packing. And we have considered that the edge of the cube, this is a cube, okay? So the edge of the cube is A. We have considered it. So we'll write here, let R be the radius of each atom and small r be the radius of octahedral void, okay? Octahedral void. Got it? Let r be the radius of each atom and small r be the radius of octahedral void, okay? Got it. Next, let A be the edge length of the cube. So the edge length of the cube, so all the sides it will be equal only, be A. Now what we are writing, we can say that in triangle ABC, okay, in triangle ABC, AB will be equals to BC equals to A. Okay, because it is a edge side of a cube, so side of a cube is always equal, okay? Side of a cube will be what? Equal only, so it will be A. AB plus BC equals to A. We have written that. Now what we are going to find out? The diagonal AC. So this is what? This is a right angle triangle ABC or not? So you will write here using Pythagoras theorem. So when I use Pythagoras theorem says hypotenuse square equals to base square plus perpendicular square. So base is this, perpendicular is this. Okay, so what is our hypotenuse? AC. So we'll write here AC square equals to base is what? AB square, and perpendicular is what? BC square, right? So we'll write it here BC square. Now AB value is how much? Look at the diagram. AB ka value is A, so A square. BC ka value is also A, so A square. So finally you will get AC square, or AC square equals to 2A square. So AC will be equals to, this square will come this side, so it will become square root, so 2A square, so which is equals to A root 2. So we got AC equals to A root 2, okay, in term of edge length. Got it or not? Understood this one? Okay, fine. So you can take it down, this one, pause the videos and take it down. We can write it here in term of edge length. Okay, edge length. This is in term of AC value in term of edge length. Okay, dear students. So fine. This one you can write it as equation 1, and this one you can write it as equation number 2. Okay, so pause the video and take down. Now I'll move on to the next step. Now this was AC ka value in term of edge length. Now we'll find out AC value. AC is equals to in term of radius. So AC is equals to what? We can write it in term of radius, capital R, small r, capital R. So we'll write here R plus small r plus small r. 2r will be there because it is a diameter. So R plus R, void ka, and plus outer radius. So this one, this is the AC ka value. So you write here in term of radius. Okay, so I hope you are not getting confused. So AC equals to 2r plus 2r, which is equals to 2 capital R plus small r. This is equation number 3. This is the value of AC. Equation number 3. Now AB in term of radius. So AB ka value in term of radius will be what? R plus R, R plus R. So it will be equals to 2R. Equation number 4. Okay, you got it? So now what we'll write? Dividing equations. Okay, dividing equations. Dividing equations 2 by 1 and equations 3 by 4. So remember, look at very carefully, dividing equation 2 by 1, okay, and equations 3 by 4. So when we do so, what we will be getting? Dividing equations 2 by 1, okay, by 1. So 2 is equals to what? AC by AB, and here also 2 is equals to AC by AB. So when you see equation 1, it's okay, no need to write this one, directly you write dividing equations 2 by 1. So equation 2 by 1, equation 2 is what? A root 2, and equation 1 is what? AB equals to A in term of edge length, and this side in term of radius, what is AC? 2R plus R by 2R. Got it? So this point is clear. Okay, dear students. So A cancel, 2 cancel. So here you will get root 2 by 1, and here it is R plus R by R. So this one, once again, what you will do? You will divide this R plus R by R. What does it mean? Once we have to divide it by capital R, once we have to divide it by small r. So R divided by R plus small r divided by R. So it will come R cancel. So 1 R plus R. Got it? Okay. Now next you bring this one this side, so it will become what? Root 2 minus 1 r by r. Okay, so all of you take it down, this one quickly, pause the video and take down. Okay, because if I write in the bottom it may not be visible to you, so I'll rub it. In the next step, what you will be doing, okay, so in the next step, dear students, it will be root 2 value is how much? 1.414 minus 1 equals to 2 by r. Now some of you might be thinking, what is the value of root 2? You have to remember, dear students, you are at class 12. Okay, so 1.414 minus 1, it will be equals to 0.4 equals to r by r. Now you cross multiply it, then radius of octahedral void is equals to 0.414 times of capital R. So this is the relations between octahedral void and radius of an atom. So for doing this one, dear students, you will be getting around how many marks? You will be getting around 3 marks in your board examinations. Okay, so it's very easy, just you have to practice it. Okay, so pause the video and take down. Okay, dear students, this class we will be winding up here. Okay, in the next class we will be deriving the relationship between the tetrahedral voids. That is also one important derivation from this chapter. And then so we will be going for coordination number. What is the coordination number of different compounds? We will be seeing all those things, and we will be solving some previous year question papers as well as NEET JEE question paper also. We will be solving it. Okay, so up to this I want all of you to be very much thorough with it, go through it, practice it, take down the notes and make a note. Okay, making note of your own is very important. Okay or not? So make a note whatever things I'm giving to you. If you find it is important, so you take it down and make a note which will you refer in during the examinations time. Okay, got it? Take these classes seriously and try to practice it, dear students, properly, because if you will not practice properly, then things will turn difficult. And if you really want to get the benefit from this channel, then please subscribe the channel and share the video with your friends, because all the chapters we are going to cover in the revisions before your exams, that is before March, we will be finishing up all the chapters revisions. Okay, dear students, so thank you so much and keep studying hard.